Let's go over the answers to worksheet 4. We're going to be investigating reflection and refraction. And this goes over the Ripple Tank Lab, parts 2 and 3. So first, let's look at reflection. How would you describe the term water wave reflection to a non-physics type? Remember that reflection is nothing more than energy or a wave bouncing off a barrier. How does the incident wave velocity and the reflected wave velocity compare? They're the same velocity, and we know that they're the same velocity because we didn't change the medium. The only thing that affects the speed of a wave is the medium. What's the purpose of drawing in a normal line in a wave reflection diagram? The normal line is very important. In fact, here's a normal line right here. Notice how that normal line is drawn. The normal line is drawn perpendicular to this surface. That's how you always draw normal lines, perpendicular. And the reason why we do that is because when you measure the incident wave, remember the incident wave is the wave that comes into the barrier, and the reflected wave is the one that leaves the barrier. When you measure those angles, you're measuring the angle with respect to that normal line. Or another way of saying that is, when you give the angle measurement, it's always between the ray or the wave and the line. Between the ray or the wave and the line. How does the incident angle of a wave compare to the reflected angle? Well, theta means angle, so we say that angle I equals angle R. Or the angle that it comes in at is the same angle that it leaves at. They're equal to each other. What is the relationship you observe between the shape of the barrier and the reflected wave bouncing off the barrier? Well, the reflected wave takes on the shape of the barrier. Let's look at these examples. This is a concave barrier, so when the wave comes in and strikes it, the reflected waves take on that shape. They become concave. In this situation, this is a flat surface or flat barrier, so when the waves come in, they strike it and they leave also flat. So the reflected waves take on the shape of the barrier. Okay, let's diagram some waves. This is reflection off of a straight barrier. Remember that IWF is the incident wave front. That's these things. That's like looking at a crest, a crest, a crest, a crest. So that's incident wave front. Incident wave direction are these arrows. It's showing you the direction that the energy or that the wave is traveling. I is incident and R is reflected. So notice the incident wave comes in, it strikes a flat barrier, and it bounces out flat or straight. This is the reflected wave direction, and these are the reflected wave fronts. Okay, now we have an incident wave striking a barrier at an angle. Remember that the incident angle equals the reflected angle. So you would draw a normal line that's perpendicular and you would approximate the incident wave coming in at the same angle that it leaves. So here is that normal line. Always draw it perpendicular to the surface. The angle it comes in at is the angle it leaves at. And the angle is always measured again between the wave and the normal. Between the wave and the normal, never between the wave and the surface or the wave and the barrier. It's always measured from the wave to the normal. So when that's drawn in, the angle measurement we're talking about is this angle right here. This is the incident angle, and this is the reflected angle. All right, now let's look at reflection off a curved barrier. Notice this is convex. When this wave comes in, it bounces back and it takes on the shape of this barrier. These waves are now convex, or they diverge. They go apart from one another. This is diverging waves. Now, when this incident wave strikes this barrier, since the barrier is concave, the reflected waves are also concave, and they converge at this point. this would be the focal point. And don't forget that your drawing needs to have incident wave front, incident wave direction, reflected wave front, and reflected wave direction. All right, task 3, refraction. Notice we have a deep region of water and a shallow region of water. Refraction is when a wave enters a new medium. And in the case of water, the way water enters a new medium is it changes depths. What's the definition of refraction? Like we said, when a wave enters a new medium. And in the case of water, it's when a wave changes or when the water height changes. Where is the wave speed the fastest and the slowest in a water wave? Well, here's where you can use some alliteration. I like to remember that shallow and slow both start with S. So deep water is fast and shallow is slow. And the equation that we'll be using is the velocity of a wave is equal to the frequency of the wave times the wavelength of the wave. So now if we diagram here, this is deep water and this is shallow water. Remember, shallow means slow. So as the wave enters this new shallow medium, it's going to slow down. So the velocity goes down. The frequency has to stay the same because the rate at which these waves are entering, that can't change. So whatever's generating these waves, maybe it's the wind in the ocean or something like that, that can't change. So the frequency or the rate at which they enter this new medium will not change. What will change will be the velocity and the wavelength. So notice that if frequency stays the same, if velocity goes down, the wavelength has to go down, and that's why we draw these waves closer together than what they were up here. Now we're going shallow to deep. Remember that deep water is fast water. So if the velocity gets big, remember the frequency has to stay the same, the wavelength also has to get big. If you'd like, you can even plug some imaginary numbers in here and play with that to see how that works out. But notice as it gets faster, the wavelength gets longer, or the space between these wave fronts increases. Okay, now we have a wave going from deep water to shallow water, but it's at an angle. So first, like we saw when going from deep to shallow, shallow means slow, velocity goes down, the wavelength gets shorter. That's why these are drawn closer together. But we also have to consider that it's going in at an angle. When it goes in at an angle, the wave is going to bend. So this is our normal line. Notice the normal line is drawn perpendicular to the surface. It's always drawn perpendicular. The incident wave comes in, and if it wasn't going to bend, it would go straight through like this. But it does bend. It bends towards the normal. So notice, like I said, if this was going to just continue through straight, it would go like that. But it doesn't. It bends towards the normal line. Anytime you go into a slower medium, it always bends towards the normal. If you go into a faster medium, it bends away from the normal. That's what we see here. We're in a shallow medium, which is slow. We're entering a deep medium. So when we go into the deep medium, the wavelengths get longer. And if we draw on the normal line, so the normal line would be sort of right here. We've drawn it in over here for you. Notice that it doesn't just go straight through. If it went straight through, it would look kind of like that. But it bends, and it bends away from the normal. And you know it bends away from the normal because anytime you enter a faster medium, the wave always bends away from the normal.